Okay, so our next section is going to be all about conjugate addition reactions. But before we get too far, I just wanted to go over a little bit of review. And I wanted to go over what it means to be conjugated to begin with. And if you remember, a conjugated system is a system where you have alternating double, single, double bonds. So really, these are unique because we've got continuous p orbital overlap between all of these carbons. So we covered this previously, but now it's coming into play in a new context. And these are unique because unlike unconjugated systems like this, these conjugated molecules have that p-orbital system where we have a lot more resonance, right? In this system right here, we can't have resonance because there's an sp3 carbon in the middle. So this would be called an isolated molecule. So this would behave more like a traditional alkene than a true conjugated system. All right, so let's take a look at how this impacts what we've recently been learning about. Well, we've actually seen a number of these conjugated systems in this chapter without realizing it. So for example, when we did aldol condensations, we made alpha, beta, unsaturated aldehydes and ketones, right? So in this case, we've got a double, single, double bond right here. So this too would be conjugated. Versus some other ketone, like this would not be conjugated because just like above, we've got an sp3 carbon in between. So this would just be called an isolated system. All right, so let's consider this conjugated system. And like I said, these are special due to their resonance. So let's take a look at the resonance forms. And these are more important for conjugated systems containing oxygen because we're not really violating that rule where I said don't draw resonance forms where you've got carbons with the positive and carbons with the negative, right? So let's take the molecule that I just showed you and draw out all of the resonance forms. Well, one's pretty simple. We could just pull electrons up to that oxygen. And as you can see, we're not violating any of our resonance rules. We don't have a carbon with the positive next to a carbon with the negative, so this is allowed. And then we can pull this pi bond over. And that would give us a double bond right here and a positive charge right there. So really what we have are three major resonance structures, or three significant resonance structures, I should say, for this original ketone, right? And it's interesting because if we think about the hybrid form, we've got partial positives on two different sites. So let's go ahead and draw the hybrid. And whenever I draw a hybrid structure, I just draw my sigma bonds first, and then I do dashed lines for bonds that are in between a double and a single bond. So for example, this is a double bond here, but a single bond here, which means that in its hybrid form, it's going to be kind of in between. Same thing with this bond. It's single here, but double over here, which means that bond must be kind of in between. So I'm going to draw that as a dash bond too. And, oops, I forgot that carbon. If we look over here, it's double here, but single here. So it looks like this must be in between as well. All right, so we've got this kind of delocalized pi system. Then we could say, well, this oxygen's a negative in some, but neutral in others. So it's going to be partial negative. And then underneath here, this carbonyl carbon is partial positive. And this carbon's partial positive. So this is really more of an accurate view of what's going on in this molecule, right? We've got areas of high electron density and areas of low electron density. And let's imagine that we have some sort of nucleophile, right? This nucleophile has a negative charge. We could then ask ourselves, well, where is this nucleophile going to attack? It could actually attack one of two different sites. It could attack right here, or if we have a nucleophile, it could attack right there. So the question is, will it attack both? Will it attack one over the other? Or will it attack the other one over the other one, right? It's kind of hard to tell. So let's take a look at some general guidelines for predicting where these nucleophiles will attack. And this is just kind of basic, and then we'll get over or get into this in a bit more detail. So general guidelines. All right, the first one is that strong/unstable nucleophiles prefer to attack the carbon in the CO double bond. So this unstable nucleophiles prefer to attack the carbonyl carbon. And what I mean by that is that's the carbon in the CO double bond, right? So it's going to attack right there. If we kind of put this into perspective, the carbonyl carbon in the above compound is going to be that carbon that's attached to oxygen. All right, so if it's unstable, it prefers to attack there. However, if you have a stabilized nucleophile, meaning one that's got maybe some resonance or something in it that's stabilizing that negative charge, stabilized nucleophiles will attack the other site. They prefer to attack the beta position. And like I said, that other carbon, if we're keeping track, is the beta carbon on these molecules. So it's kind of interesting. We have to think about the strength of the nucleophile. Something that's really unstable, like a Grignard reagent, is going to attack directly into the carbonyl carbon. But if you've got something that's stabilized via resonance, it's usually going to attack that beta carbon with very few exceptions. All right, so let's take a look at how we prepare these alpha-beta unsaturated ketones or aldehydes. And what I mean by that is, how do we prepare this conjugated material? So preparation of alpha-beta unsaturated ketones or aldehydes. Oops, clean this up. And this is just review from what we saw before, but you can do the Aldol reaction, where you have an aldehyde that essentially reacts with itself using sodium hydroxide and heat, and it's this heat that's going to favor formation of that double bond. So what we're going to get out of this reaction is going to be something that looks like this, where we've got this alpha-beta unsaturation. And like I said, this is conjugated. We've got the alternating double single bonds. So let's take a look at an example. So like I said, if we have a Grignard reagent, like methyl magnesium bromide, followed by an aqueous workup, this is going to prefer to attack the carbonyl carbon, because Grignard reagents are just unstable. So we can go ahead and we can say it's going to look more like this, where we're going to get this methyl group right here installed off of this position. So we're able to form an addition product. In this case, it's kind of weird to think about, but if we think about the two things that were added, we added this methyl group, and we also added in this hydrogen. And if we think about their relative positioning to one another, we've got one atom followed by a second atom between them. So this is simply referred to as 1,2 addition, because our two new groups are going to be installed with two atoms in between them. All right, let's compare this to a different nucleophile. If we want to use a more gentle nucleophile, one that's less aggressive than a Grignard, we could use that lithium dialkyl cuprate, the Gilman reagent. If you recall, this was the same reagent we used to add in some sort of alkyl group to an acid halide. However, we can use it in this context as well. It's a lot more gentle. It's the reason it didn't add into alkyl halides twice, right? So if this happens, it's going to prefer to attack the beta position. And if we do this, we're going to get a new product, but the carbonyl is going to stay put. And we're going to get this methyl group installed off of the beta position. And if we think about the other group that we got installed, it's going to be the hydrogen right there. So that's where we added those two groups in. But if we look at this, it's different than the other one because now we've got 4 atoms between the methyl group and the oxygen. So this is just referred to as 1,4 addition. All right, so it really, like I said, depends on whether or not you're using a strong nucleophile versus a weak nucleophile. Weak nucleophiles tend to give you 1,4 addition. Strong nucleophiles give you 1,2 addition. All right, so that's where we're going to stop now. This is just a brief introduction, but when we come back, we'll see this used in a variety of new contexts.